The box and whisker plot gives us a great visual representation of a lot of the key metrics that we'd like to see on a distribution, such as the median and the quartiles, as well as outlying data points. Up until this point in the notebook, and I think up until this point in the Machine Learning Foundation series overall, we've always been plotting using Matplotlib. But there's another great plotting library called Seaborn that creates some beautiful plots, and we're going to start using it a bit now. So you can set particular styles with Seaborn. And so here I'm setting the style to a white grid style. And then we can very quickly create a box plot in Seaborn. And so we're telling the box plot method that the x argument of the method is equal to x. And so x, again, is that same distribution that we've been plotting in many of the last videos. So let's run that, and here we go. So this is a box and whisker plot. So it's got the box, and it's got whiskers. And it also has these outlying data points here. So let's talk about all of those elements. So the edges, as well as the midpoint, this line in the center of the box, are determined by the quartiles. So the median, the 50th percentile, is about 0.7. And then this value here, this bottom value, is the 25th percentile, 0.32. And this is the 75th percentile, 1.19. So those are the same 3 points, those 3 values that we plotted up here when we first learned about the quartiles. All right, so back to our box and whisker plot. The box edges, in more technical terms, define what's called the interquartile range, or the IQR. So that's this range spanning the 25th percentile through to the 75th percentile. That's the interquartile range. And so that value, that's a specific value. So we can take that 1.194 and subtract 0.325 from it. That gives us what I'm calling R here, our interquartile range of 0.869. So the reason why we're calculating this interquartile range is because the whisker lengths, so the lengths of these whiskers, are determined by the furthest data points in our distribution that are within 1.5 times the interquartile range. So in this case, with our particular distribution here, the lower whisker could stretch as far down as 0.325 minus 1.5 times that interquartile range. So 0.325 minus 1.5 times that value R. So the lower whisker could stretch as far down as negative 0.98, roughly. And the lowest value of all of the values in our distribution is actually inside of that. So the lowest whisker is plotted where that lowest value is, at negative 0.17. So that's where our lowest whisker is here. Now for the highest whisker, we have a different kind of situation. So let's calculate the highest value that the upper whisker could have. So the upper whisker could stretch as far up as 1.194 plus 1.5 times the interquartile range. So where am I getting those values? From that 75th percentile, from the edge of the box. So it could stretch from 1.19 plus 1.5 times the interquartile range. And that value comes out to 2.5 roughly. So that's the furthest that this could possibly reach out to is 2.5. Now, there are several values. Specifically, I know that there's 11 values beyond that threshold in the distribution. So those values beyond that upper whisker are considered to be outliers. And so we plot them as individual points. So if I sort our vector x that contains all of the points in this distribution, so all of the points in this distribution, if I sort all of those values and I look at the final 15 of them, you can count up that 11 of those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of those values fall outside the highest possible value that the upper whisker could have. So the 12th highest value, this one here, 2.435, that is the largest value in our distribution within the upper whisker's maximum reach. And so that's where the upper whisker is plotted. So it's plotted at 2.4, so that's where the upper whisker gets plotted. And then the 11 other points, those 11 outliers outside the upper whisker, get plotted as individual data points. So useful for examining distributions all on their own, box and whisker plots are especially helpful for comparing distributions. So even just being able to look at this distribution, we get a lot of information about this particular distribution by looking at this single box and whisker plot. But they're even more useful when we compare multiple distributions side by side. So let's load in this data set called the iris data set. So it contains 150 rows of data, and each one of those rows corresponds to some measurements about an iris flower. So there are 3 species of that iris type of flower, and there's 50 observations of each of the 3 species. And for each of those species, we have 4 measurements. So petals, I think most people know what petals are on a flower. They can be the brightly colored part of a flower. So yeah, the petal. I think everyone knows what a petal is on a flower. But the sepal is something that people might not know. So the sepal is, it's green in color and it occurs right under the petal. So it's uncolored part of the flower. So we have, for every one of these 150 iris flowers, we have a measurement of the petal length, the petal width, as well as the sepal length and the sepal width. So we can pass our iris data set right into the box plot method. And it very conveniently, we haven't asked for any particular kinds of breakdowns. So we haven't specified that we want it broken down by species or anything like that. So Seaborn assumes that what we'd like to see is these 4 columns as separate box and whisker plots. So we can see from looking at this that the sepal length has the longest median value relative to sepal width or petal length or petal width. We can also see that sepal width has less variance, that those sepal width values are closer to the median than, well, any of the other distributions, but particularly the petal length. So petal length, we can see, has the most variation. So that gives you a sense of how box plots can be used to give us a lot of information about a distribution of data points at a glance. And as one more nifty example, let's load the tips data set. So this contains 244 observations of tips that a server receives. And so there's information about that meal. So we have what the total bill came out to, we have what the tip was, we have the gender of the person serving, so was it a waiter or a waitress? We have information on whether the table had a smoker or not, what time of day it was, so was it dinner or lunchtime, what day of the week was it, and then also what was the party size. So we have all this kind of information that we can use to slice and dice this tips data set. And so to show you the power of this Seaborn box plot method, I'm passing in a number of arguments to break the data down. So along the x-axis of our box and whisker plot, we are providing the day of the week, so Thursday, Friday, Saturday, Sunday. Along the vertical axis, we have what the total bill came out to. So that's where we're really seeing the box plot. So the median of the box plot tells us a measure of central tendency of what the total bill was on any given day, broken down by whether there was a smoker at the table or not. And so, for example, we can see that on Friday, in this particular data set, the tables that didn't have a smoker had a median total bill that was larger than the tables that did have a smoker, even though the single table that had the highest bill that day was a smoking table. So there's another example of how box and whisker plots can at a glance provide you a lot of information about the distributions in a data set. Nice, so we've spent a lot of time talking about box and whisker plots, obviously, and most of the time we've been talking about measures of central tendency, so things like the median. But as I've been describing this box and whisker plot, I've been talking about variation in the data. So, we can see that on Saturday and Sunday, it looks like we were getting a wider range of total bills than we were getting on Thursdays and Fridays. So the whiskers stretch a lot farther on Saturdays and Sundays than they do on Thursdays or Fridays. So that kind of general notion, that kind of dispersion of the data, we can quantify that very specifically. And up next, we're going to talk about the most common ways to measure dispersion.